So we start again, and the next speaker is Gian Giudice on high energy physics and the European strategy.
Thank you very much. On March 7, 1960, Bruno Touschek, then a researcher at the INFN laboratory in Frascati, gave a talk proposing the idea of a collider. It was a bold and ambitious proposal at that time, but under the motto probare and reprobare, the idea worked. So more than 60 years later, Touschek's idea is still at the base of the most effective instrument at our disposal to investigate the world of elementary particles and explore the structure of space-time at the smallest possible distance. I have never met Touschek. He died when I hadn't even started to study in university, but he's always been an inspiring figure for me. The tragedy of his life because of the atrocious madness of anti-Semitism, which is a virus still present today in our society. And but I see also in Touschek the pure genius of the scientist, and also ironic and witty human being. So all these are great qualities for a physicist. In a sense, he was a worthy successor of Fermi because he belonged to that generation of physicists for which the separation between theorists and experimentalists was not well defined. Indeed, he worked on many aspects of quantum field theory, and one aspect was CP, CPT, and time reversal. And I like when I read the anecdote about time reversal. So after a car accident, Touschek was brought to the emergency room at a hospital in Rome, and as usual, the doctor asked him some simple questions to check if the patient suffered from brain damage as a result of the accident. So the doctor asked Touschek, what was he doing for a living? And Touschek replied, I'm thinking about temporal inversion. And with this, the medical examination ended, and Touschek was immediately hospitalized with a diagnosis of serious concussion. 60 years later, colliders have really revolutionized our understanding of the microscopic behavior of the physical world. The field went through great discoveries, periods of confusion, unexpected results, and brilliant breakthroughs that revealed an order in nature. And so all this has matured into a beautiful conceptual structure, which we call the Standard Model. The theory is truly a monument of human scientific achievement, since we are able to understand the building blocks of matter and forces in terms of a geometrical principle, which is called gauge symmetry. And it appears that gauge symmetry dictates the properties of all fundamental forces, gravity included. But the story of human discovery is not over. As long as civilization exists, we will always ask more and more fundamental questions about the origin of matter, of the universe, of space-time. And these questions still motivate particle physicists to continue their quest. The experimental tools at our behaviors have certainly grown enormously since the time Touschek gave his visionary talk about colliders in Frascati. But colliders are still a central instrument for our field. So Touschek's legacy is still alive today in the program of future colliders. Touschek was a person that didn't look at the past, but probably was always looking at the future. So, but before, however, I discuss my views on future collider physics, I would like to ask one question that we should always keep in mind, which is, why do we want colliders? Our society, our planet are going through unprecedented challenges, epidemics, poverty, sustainable and clean energy production, clean water supply, global warming, environmental protection. So given all these pressing issues, our colliders really are a priority for society. So this question is crucial, and first of all, science is key to addressing society urgent challenges. Of course, the scientific effort should focus on the most urgent issues that impact society, but investing only on specific targets is a short-sighted strategy. And as shown repeatedly in history, it is not an effective strategy. Focusing only on applied research simply doesn't work. Fundamental research is a necessary driver of innovation. Investment on fundamental science, which are comparably small on a macroeconomic level, can have a vast impact on the future of humanity. And I think Manuela did a fantastic job in the talk presenting this. But let me just give you an obvious example. So the global emergency that we live in today, caused by the COVID-19 pandemic, has taught society the value of science. And particle physics cannot produce vaccines, but has produced a web which was instrumental for society to survive during the COVID-19 crisis by allowing the continuation of economical activities, global coordination, communication, and social relations. You can understand, I have children who don't live with me, and so I know what that means. CERN developed the web having the particle physicist needs in mind, not the problems of society. But just think what would have been the impact of the COVID-19 pandemic if CERN hadn't developed the web for particle physics. Many technological advances of great benefit to society have come and will come from fundamental research, which is targeted to problems that have nothing to do with society. So new technologies will be developed, and new colliders require the development of a new generation, for instance, of high field superconducting magnets, and research in the direction of high temperature superconductivity. So there's really a lot that the technology developed for colliders can offer society. Fundamental research also channels human talent and creativity towards complex problems, whose solution lead invariably to unexpected applications. So we rarely can predict what they will be, but these applications unfailingly happen. And as also Manuela said, another byproduct of collider physics is scientific training. All these students which are trained to work in close contact with advanced technologies to develop the ability of problem solving will serve society, even if they don't go in academia. And another more subtle aspect that I would like to emphasize is ethical values. So practicing science teaches to develop certain principles of tolerance, of respect, of fairness, of justice, that make better individuals, that trains to be better individuals for society. Of course, the aspect of fundamental research that is closest to my heart is human knowledge. So understanding nature, understanding the universe, understanding physical reality have an immense value for humanity. So the scientific exploration of the unknown has an extraordinary inspirational effect on the public. And this is a powerful driving force for civilization. So humans simply cannot give up their intellectual curiosity to understand the world they live in. And knowledge, scientific knowledge, is CERN's primary mission. So CERN is focusing on fundamental research in particle physics, but CERN is not blind to societal issues. So environmental sustainability is the biggest challenge that our society has to face today. And as scientists, we cannot remain indifferent to these problems, and our way of operating has to change accordingly. So particle physics should not simply adapt to societal changes, but should lead them. The tradition of particle physics is always to be at the forefront of changes, whether in scientific issues, information technologies, and also community practices. So CERN is well aware of the challenge posed by environmental sustainability, and it is taking a leading role in the changes that we need to tackle. This plot shows the steady growth of CERN investments in projects related to environmental protection. So when it comes to large collider projects, our concern is always to scrutinize them carefully in terms of their environmental impact. And for instance, there are studies which include R&D on new environmentally friendly gases for the cryogenics of particle detectors. Another point is energy saving and reuse. This means reviewing the energy consumption of various projects, heat recovery from computing facilities. This has already been taking place at CERN, and converting it to heating for buildings during winter. R&D on efficient power production with potential applications in industry. And the third point is to develop technologies useful to protect the environment. And you heard from Manuela some highlights. And there are of many cases. Of course, the goal of collider research is the exploration of the particle world. And as I mentioned before, today we have consolidated a fairly satisfactory description of nature at the fundamental level, which is given by the Standard Model plus general relativity. So is this a final chapter of the story? That's certainly not. Any scientist can tell you that. While it is a perfectly consistent theory, the Standard Model cannot answer more structural questions about the origin of the underlying theory. Some of the most puzzling aspects of the Standard Model come from the Higgs boson. The Higgs boson was discovered almost 10 years ago, although it was first proposed by theorists at the time that Touschek was pioneering the idea of particle colliders. Now, the experimental data that we have gathered at the LHC match very well the theoretical prediction for the Higgs boson, but the underlying nature of this particle remains a mystery. Its structure does not seem to follow the same fundamental principles that determine the other particles in the standard model. This is why theorists are very much puzzled by even by the existence of the Higgs boson. And most of us believe that the Higgs boson must be only the tip of a more complex phenomenon, of a more complex structure, which is still unknown to us, and is submerged beyond the frontier of our knowledge. So during the last decades, theorists came up with many new creative ideas of what could be this submerged world, or what could lie beyond the Higgs boson. And many of these ideas are terribly stimulating, introducing new kinds of forces, new particles, new symmetries, and even a new concept of space-time. And these ideas were put to empirical test with the experiments at the LHC. And however, none of these ideas were shown to be true. Now, some people see in this result a failure of particle physics. I see only a success of the scientific method, which is based on theoretical hypotheses followed by experimental scrutiny. And the result of the LHC give only more reasons to pursue the search. Actually, as a theorist, I think that the situation in particle physics today is only more interesting. What the LHC results are telling us that once again, nature hides surprises. So the next layer of physical reality is very different from what we had imagined so far. So the game for theorists is only becoming more intriguing. What we need is a radical change of paradigm, a revolutionary new vision of nature at small distances. And I'm sure that this is a challenge that Touschek would have loved. And this is a great challenge for the young generation of particle theorists today. Some new theoretical ideas are already starting to emerge, but it's still too early to tell if any of these ideas is really promising and could be a serious candidate for resolving some of the mysteries left unexplained by the standard model. Of course, theory alone will never be able to tell if an hypothesis is correct or not, and we need more experimental results. And needless to say, CERN has a thriving experimental program that tries to tackle the fundamental open questions in particle physics today. In the short term, the CERN scientific program has 5 main objectives. The first objective is a successful run 3 of the LHC. The LHC operates in alternating phases with some years of data taking and some years of maintenance and upgrading. And today we are here. So the long shutdown 2 has been completed, and recently pilot beams have already been circulated successfully in preparation for run 3, the next phase, in which ATLAS and CMS are expected to collect at least as much luminosity as in the previous run, and LHCb and ALICE are expected to increase significantly their data set. So after a risk assessment study, it has been decided that the optimal energy for the upcoming LHC run will be 13.6 TeV, which is slightly higher than the previous run, but not yet at the target of 14 TeV. The second objective is the completion of work for the high luminosity LHC and the required upgrade for the detector. So the high luminosity phase is what follows run 3, and it will increase the total number of recorded data by a factor of 10. This will allow LHC physics to enter an era of precision measurements that will give us a lot of important information. So the high luminosity LHC is expected to start operating, let's say, in the late 20s. The third goal is to reinforce a scientific diversity program. A high energy collider program is not sufficient to tackle the many open questions in particle physics. More and more, we need a variety of experimental strategies and approaches. A very constructive synergy is building up between particle physics and neighboring fields. I'm thinking about observational cosmology, multi-messenger astronomy, underground dark matter detection, gravitational waves, nuclear physics. But new experimental techniques are starting to emerge from the search for light dark matter particles and feebly interacting particles. And it is exciting to see new ideas borrowed also from atomic physics or condensed matter physics. The fourth objective is the support of neutrino experiments in the US and Japan through the neutrino platform. And in particular, CERN is constructing the cryostats for the June experiment. And last but not least is theory. Theory remains a priority for CERN. I am quoting the words from the CERN Director General when she said, "Theory is essential to open new avenues of exploration and motivate experimental investigation. CERN will continue to support a broad range of studies related to the lab's experimental program and beyond." I want to underline the word beyond. In the way I conceive the CERN theory department, it is important that we develop a broad and free research program, not limited to direct support of the experimental program. But CERN and the particle physics community in general is looking beyond the short term and dreams about the future. This dreaming is done in a coherent and inclusive way through the European strategy for particle physics. This is a community-driven exercise which first took place in 2005, and then it has been updated twice at intervals of about 7 years. So the last update took place in 2020, and I had the privilege of participating as a CERN representative. It was a particularly important event because the particle physics community is at a critical moment when decisions about the long-term strategy have to be taken. So the process of the European strategy involved an open call for proposal, then preparatory work in which the physics case was outlined in a briefing book, and a general conference in which the community got together and to discuss the issues, and finally a one-week closed session where the representatives of each European country and the major labs were present, and where the final document was written. Let me just tell you the main point that emerged from the European strategy, especially in view of the future collider research. So from the physics point of view, the recommendation covered 3 points. One, an electron-positron Higgs factory is the highest priority next collider. Number two, for the long term, the European particle physics community has the ambition to operate a proton-proton collider at the highest achievable energy. Three, a diverse program that is complementary to the energy frontier is an essential part of the European particle physics strategy. So the discovery of the Higgs boson was a milestone in the history of science, but he has left us with many unanswered questions. The true nature of the Higgs boson is a big question mark for particle theorists, for particle physicists. So, and luckily we have the means to gain further information about its nature, and this can be done only by measuring its properties with higher and higher precision. At present, we know the couplings of the Higgs to gauge bosons at the level of, say, about 10%, and the coupling to third generation fermions at the level of 20%. But the targets of future Higgs factories are more ambitious. The goal is to go below the percent level. So this corresponds to testing a possible substructure of the Higgs particle up to a distance of 10 to the -5 the proton radius. So this is really probing the intimate structure of the Higgs boson and tell if this particle is a composite particle or a truly elementary object. We also want to probe the couplings of the Higgs to the second generation fermions, which can give us information about the mechanism that feeds mass to matter. And we want to test the invisible decays of the Higgs, which could give us information about the nature of the dark matter. We want to test the Higgs coupling, which gives us information about the nature of the electroweak phase transition. And we want to test possible rare Higgs decays, which give us information about the symmetries of the standard model. So the experimental program of Higgs precision measurement goes straight into the heart of the origin of electroweak symmetry breaking, which is still an open question in particle physics. How can we do these measurements? Well, there are several proposals around the world. Other speakers will tell you about the projects in Japan and China. As far as CERN is concerned, we have two projects on the table. One is a linear ± collider, which can be extended in stages with a first stage in which the tunnel length is 11 kilometers and the machine operates as a Higgs factor. But the tunnel can be extended, and with the energy increasing accordingly to explore also the high energy domain, and justification of this phase could be linked to possible discoveries at the LHC or indication from the LHC. This project is called CLIC, and Steiner will talk about it, and the price tag of the first phase is about 6 billion Swiss franc, and another 12 billion have to be added to get the full scale 50-kilometer tunnel. The second proposal is called Fcce, Future Circular Collider. Essentially, it's a way of repeating the successful story of LAB and LHC at a larger scale. So the plan is to have a new tunnel, about 100 kilometers long, now I think a little less, which will host first an E ± collider and then a proton-proton collider. The first stage has a price tag of almost 12 billion Swiss francs, out of which almost half go into the digging and the tunnel infrastructure directly into industry. In terms of precision, this machine would be really a wonder, producing 1 million Higgs bosons and 10 to the 5 more Z bosons than the full lab program. So the next stage of the Fcce would accomplish what the European strategy defined as the ambition of the European particle physics community to operate a proton-proton collider at the highest achievable energy. So if the 16 Tesla magnets of niobium-3tin superconducting materials are put into the Fcce tunnel, one could build a hadron collider operating at about 100 TeV. And with high temperature superconducting material, one could dream of even higher energy, say 150 keV. But even with regular 6 Tesla niobium titanium magnets, one could already do as well as the SSC. So the price tag is in the range of 17 billion Swiss franc, where most of the cost comes from manufacturing the magnet. Another priority identified by the European strategy is accelerator research with special emphasis on new technology. Along this line, the CERN has doubled the budget on new accelerator projects. The most prominent is the AWAKE project, which develops a new plasma wake field acceleration. And new investments are made also for a far future muon collider, which could be possibly hosted in the Fcce tunnel. What's lacking any precise hint for the scale of new physics from the LHC, we need to have a broad and ambitious research program. So we need, on one hand, to explore as deep as possible with the highest possible energy allowed by the new technologies. On the other hand, we also need to broaden the research program using a variety of different techniques, as indeed was recommended by the European strategy. But it is clear that in this broad landscape of research that covers different fields, colliders remain irreplaceable tools. For example, the Higgs boson could have been discovered only through colliders. No other experimental tool or technique could have led to this discovery. But increasing the energy is not the only leverage at our disposal for gaining new knowledge. I think that a crucial lesson learned from the LHC is that hadron colliders are not only discovery machines, but are also excellent precision machines. And this result could have not been anticipated at the time the LHC started, and was possible only because of the successful interplay between different elements. So unprecedented technological advancement, exceptional accelerator performances, excellent detector resolutions, high performance computing and data handling, and higher order theoretical calculations of background processes with accuracies unthinkable only a few years ago. So it was the coming together of different expertise with different scientific community was really the secret behind the success of the LHC precision program, which brought new knowledge and opened also new prospects in research beyond the traditional frontiers. So precision has become the key for present, but it will be also for future exploration in high energy physics. And there's a lot to learn from precision measurement, even without direct access to high energy processes. And a good example are some unexpected anomalies found by LHCb in the precise measurement of some rare B meson decays. It's too early to tell if these results are real and or not only some statistical fluctuation or poorly understood systematics. But lots of new data from the LHC and BEL2 will come and clarify the situation. So if true, these results would be really a revolution in particle physics, because they cannot be explained simply by a small deformation of the standard model. They would really shatter the basic structure of the standard model and imply the existence of a completely new sector of the theory. This is something to be watched carefully in the future. So Bruno Touschek was a visionary. His vision is still alive today in present and future CERN scientific programs. So my message is that research at Future Collider will boost technological developments in many fields in ways that are unimaginable without the driving force of fundamental science. But most of all, it is going to allow us to explore nature at even smaller distance scales and provide humanity with new knowledge about the fundamental principles that govern the physical world. With the Future Colliders at CERN, we are keeping Touschek's dream alive, so that some young boy or some young girl today can say what Touschek wrote in a letter to his father in 1946. Ich will ein Physiker werden. I want to become a physicist. Thank you. This is Bruno's gift to the Accademia dei Lincei, by the way. This is a lynx with 6 legs to remember the Egypt symbol.
Thank you, Gian, for this very interesting talk. I have a question related to the next European strategy. If I understand correctly, this should, the finalization of it should be made by 2025, right, which is
not the 7 years is expected 27, I would say, yes.
No, we had Granada was 2019.
Yes.
And the preparation of it was the year before.
Yes,
7 plus 2,
so
2018 is 2025.
It would start with a new mandate,
exactly,
with a new Director General.
So my worry is how much work can we perform and finalize in order to have next European strategy to consist in a kind of recommendation for a clear project.
Right.
Rather than, I very much hope, will not be another recommendation to continue to investigate, click, FCCEE, FCCHH, I don't know, whatever. Because I think if you consider that high luminance LHC will stop in 2035-36, if you consider that the first stable beams at reasonable luminosity took more than 11 years from the end of LEP, I see, a territory in the post-high luminance LHC era of many, many years with no operating projects at CERN. And I think at some point, I don't support the idea of having a plan B, but I think at CERN there are still resources to maybe perform an intermediate project in order to sufficient and successfully wait for the next big project that can be, for example, the big circular future collider.
I totally agree with you that the community cannot afford not to take a decision about the project that CERN should follow at the next European strategy. So CLIC research is, well, Steiner will talk about it, is in a fairly advanced level, and the plan will be to have a status report of the FCC about its feasibility by the next European strategy. So giving all the elements to see if the project is feasible technologically, but also financially, so there should be a complete plan. And that is a mandate of the present directorship in order to, by that time, have that document ready. As you know, it was already started. Now the body is in place. The study has started and is expected to have this feasibility study ready in time for that. Then will be also a political decision. Will the community, I'm talking about the scientific community, but also the political community, ready to take a commitment by then? I think it absolutely has to be taken. Somehow part of our community was expecting that we could have taken it already in the past one for the future. It was decided, and I think it was a wise decision, to keep several options still available, because we cannot say, for instance, commit fully to the Fcce, because we are not sure that we can bring it to completion in this phase. So it is important to have a plan B and a plan C ready in time. But for the next European strategy, a decision should be taken and then define the project and go ahead. I think it is possible from the scientific side to be ready in time. Whether Europe will be sufficiently united then to back up these projects at the moment is impossible to see. I mean, the economic situation is changing so rapidly. If we had just talked 2 years ago, we would never have predicted what happened now. And so it is, I would say, impossible at the moment to make a prediction, but also I think we should not do it. I think it is important that we don't preempt the exercise. We don't define what our priority should be before we have all the elements in place. So the feasibility study of the Fcce is a priority, should be done in an unbiased way, because as you understand, there are also communities that back up a certain projects, maybe sometimes not only because of scientific reasons, but simply because their heart is on that project. And we have to, I mean, it's human, it's normal, but we have to start to factor out that, arrive with all the elements, and take a rational decision, which is good for the community and good for Europe. Luciano.
I understand all the problem of politics and approval, but from the point of view of the technical point of view, what would be the projection times of E plus E minus and of Fcce?
Right. So there is already a schedule in place. If you want, I can show you. I have the plot. The question is, what is T0? So starting T0, saying from the moment of approval,
starting
the plan
now.
is effective. So if it would be the idea would be to leave essentially only few years between the end of the high luminosity phase and the beginning of the plus E minus machine. The community need to have continuity. We know that there is a maximum number of years that you can, of gaps between projects that you can maintain. So it has to be below 5, I would say. Otherwise, the community will not survive and keep such a long-term projects. And this is the plan. Of course, it's impossible to predict, but the plan would be to within 5 years to go ahead.
Okay, thank you. So it's my great honor, pleasure to give this talk about the circular colliders in China. Indeed, we all learned the story of Bruno Touschek, and indeed in our effort we followed very much his spirit and try to have say innovative effort to push colliders in China. So I added S in my talk, so I'm not only talking about the CPC but also talking about BPC. So accelerators in China started in 50s. So these are few very early machines built in China. So this is 2.5 MeV proton electrostatic accelerator, 30 MeV electron linac, and also 30 MeV proton linac in 80s. But in addition to these small machines, there's a lot, in addition to these small machines, the particle physics China really started in 80s when BPC was really approved. In between, there were many proposals. They all failed and never been realized. So Beijing Electron Positron Collider and the detector, Beijing spectrometer, have been in construction starting from 1984 and completed in 1988. So the machine has been running since then until now. Of course, we had the upgrade in between, starting from the year of 2004 to 2008. You can see this is a new double ring machine running at Tau Charm energy range. And this is comparison of the luminosities of different machines in this energy range. And BPC and its upgrade have been leading in the world at that time. Of course, we have other Adone and so on being pioneer of this field. So the Beijing spectrometer collaboration, or BES3, is actually a large international collaboration with almost 500 members from 74 institutions in 15 countries, many from Italy, of course. We had Ferrara, INFN, and Torino. So there were a few successful results coming from the BES3. The first one is the discovery of possible 4-quark states, ZC3900, neutral and charged, and also ZC4020, ZCS 3985, and so on. These are all very interesting results, and also got a lot of attentions in the community. We had new decay modes of XYZ particles, and also a lot of new, properties coming out from these measurements. We also had discoveries of exotic light hadrons like X1835, 1870, 2120, etc. And some of them are very good, glue ball candidate. So we are actually continue to search for glue balls and also hybrids. We also had a study of lambda hyperons and its CP phase, the neutron form factor, and also test of standard models by charm meson decays, etc. Typically, we have more than 40 papers per year up to now. We already had 360 physics papers published so far. For the future, we had, since we understood that there is a very rich physics program which requires more than 40 inverse phantom bulb data, and such quantity of data actually corresponding to 15 years of data taking at the present luminosity. This curve shows you the theoretic curve of the luminosity, and the red dots are the results, the operation status of the machine. So you can see that the peak was designed at the Psi at the Psi prime energy range. But we believe that for the higher energy, there is even more needs of physics. So we plan to increase the luminosity at a high energy by at least a factor of 3, and also increase the energy range from 2.4 to 2.8 GeV. And this upgrade is actually not so difficult. We are not going to rearrange completely the machine, but only adding RF cavities per beam. So by having this new RF cavity, we can squeeze the beam size and increase the luminosity. And these technologies are also a result of a CPC R&D effort. So these can be seen as a test of the CPC R&D prototypes. We already got approval by the Chinese Academy of Sciences, and we plan to complete this upgrade in the year of 2024. And the machine will then continue to operate until at least 2030. So what is the future of BPC2? So since 2005, we were discussing what is the future of high energy physics in China after BPC2. And there were a number of new machines proposed and discussed. And there were also ideas saying that there's no point to build such a machine in China, we should just join the IRC. And what could be the future IRC is remains open question. We still don't know whether it is going to be built or not. And also there was a problem in China that it's very hard to get support, financial support, to join a large international project. This was a problem and has been very evident for the HC. The China's contribution to HC is very limited because it's very hard to get funding support for international project. Situation has been slightly changing, but at that time, we were not confident that we can get enough support for China to join the IRC. But around the year of 2012, we were discussing what could be the future of high energy physics after the Higgs discovery. So, I mean, the new era is coming. Exactly that year, the idea of the circular electron-positron collider as a Higgs factory and followed by a possible super proton-proton collider was proposed. And this proposal quickly gained momentum in China and also in the world. The idea is to look for the Higgs properties and trying to see if there are any new physics. And if yes, we can go to the PP collider, and the tunnel can be reused for PP collision, for heavy ions, even for EP collisions, and they can all go all the way up to 100 TeV. So the idea was then quickly reported at the Fermilab Higgs factory workshop. I guess some of you probably know this workshop and have been attended this workshop. So this was in October 2012 at Fermilab. So the idea spread out quickly in the world and becomes very popular. And now there were a lot of discussions and becomes a central point for the possible future of high energy physics. The reason we look for Higgs as a first priority, as the European strategists said, is because this is a very special particle. And it's the only elementary particle with spin zero, and the only elementary particles with non-gauge interactions. And it is also directly related to physics beyond standard model and cosmology. For example, it may interact easily with dark matter particles because dark matter particles can have only the mass, as we know, and Higgs giving the mass to the standard model particles. So Higgs may have very good couplings to the dark matter particles. And also the mass of origin is known, and the self-coupling is very important. And we need to know whether vacuum is stable or not, why it is metastable. So having a detailed study, precision measurement of Higgs properties is actually a window towards the future, and it is a step which cannot be skipped. So a precision Higgs study at CPC can improve the coupling measurement of the Higgs with respect to the HC by a factor of 10, roughly. And at the HC, the direct searches didn't find any new physics up to 1 TeV. And the 10% precision of the coupling measurement of the Higgs can also allow you to probe the new physics up to the level of 1 TeV. So if you are able to go to 1%, then you can really go to something like a 10 TeV level. And indeed, this is a very important step towards the future and absolutely needed. And by having this kind of Higgs factory, you can also measure the Higgs self couplings and also Higgs to Z couplings. And this will allow you to understand whether the electroweak phase transition is which type, whether this is in this red type or this green type. And you can see from this plot, indeed the CPC can give you a very good measurement of such kind of couplings, and it can give you a very good indication whether the electroweak phase transition is the first order or second order kind of transition. And such a machine is also a huge Z factory and can give you very precision measurement of the electroweak parameters, can also probe new physics up to the TeV level. So we're actually preparing a physics white book covering Higgs physics, the electroweak physics, QCD, and the flavor physics. Some of them are almost finished, like the Higgs, and flavor is still in the preparation. Electroweak and QCD is like a little bit behind. We are actually short of manpower indeed. And the CPC can also be a very good machine for the synchrotron radiation. And this one shows you how good a CPC 100 kilometer machine can generate the spectrum of the synchrotron radiation light. The flux can be comparable to almost the best light source in the world. And also the beam energy can go all the way up to very close to 100 MeV, and the peak is 10 MeV. So by having such kind of 10 MeV, let's say monochromatic energies of gammas, you can study the nuclear physics, astronuclear physics, material science, and also you can do, say, for example, structural inspection and so on. So such kind of light source is actually unprecedented and can be studied and used for a lot of things in the community and also for other disciplines. Indeed, CPC for this kind of circular collider has higher luminosity and upgradable for the PP collider, and also it's a multi-purpose covering the synchrotron light. So this is the basic design, the double ring collider, a booster, and then a LINAC. So the baseline is 100 kilometers with 30 megawatt synchrotron radiation power per beam, upgradable to 50 megawatt, and can be upgraded to high Lumi Z, TT bar, and so on, and all the way up to the PP collider. So we have to be sure at this moment that the tunnel is built in a way compatible with the future possible future PP collider. So this is a list of the parameters. You can see the luminosity is 5 times 10 to 34 for the Higgs, and 1 times 10 to 36 for the Z. In the last several years, we have been working on the R&D and the prototypes of the machine. These include electron gun, the positron source, RF cavity system, and high efficiency CW klystrons, magnets, vacuum system, and so on. And in addition, we are working on the high TC superconducting magnets for the possible future PP collider. So let me show you a few highlights. This is the R&D effort of high Q cavity, RF cavities. One is the 1.3 gigahertz for the booster, and another type is 650 megahertz for the collider ring. And you can see the results have been obtained by using the so-called medium temperature baked or the annealing process, which can give us almost the world's highest Q value all the way up to 20-something megawatt per beam. And they actually satisfy all the current machines like the CPC, SES2, and also Shanghai free electron light source. Indeed, we are probably the only supplier in China to the Shanghai free electron light source. And this one shows the machines, the RF cavities for the IC. This is EXFEL specifications and the ISC specification somewhere here. And we are actually not very close to what we need for the ISC, but not yet there. And we're actually trying to improve the performance of high gradient RF cavities. This one shows 650 megahertz cavity. This is spec for the CPC 2-cell cavity. Our prototype already reached the specification. And then we have another different design, which is CPC 1-cell here. And this is very difficult. It's 40 megawatt per meter, and also a very high Q value. We are still working on it. If we are able to reach this one, I think CPC can be used the 1-cell cavity for particularly for the Z operation and the Higgs operation at the same time. So this is going to allow us to switch easily, even at say our kind of level between the Higgs machine, between Higgs energy and the Z energy. So easy switch between Z and Higgs is a very good property of the machine that we're trying to get there. We actually invented a new recipe to polish the RF cavities. This is called the flexible medium method. It's not very, or we call it flexible polishing. The method is to have friction between the flexible media and the cavity surface. The so-called flexible medium is just something very similar to the sand, and you can rotate your RF cavity so that this kind of media can polish the inner surface of a cavity, and then get very good roughness. So you can see this is the conventional method. You have EP process, annealing, and light EP. And by having this flexi polishing, you can actually give up bulk EP, which is a very environmental unfriendly and very expensive. And by having this new recipe, we can get very high quality kind of cavities. We're still working on it. And we believe that this method is very promising. We're also working on the high efficiency klystrons. The first prototype has been successful. The efficiency is 62%, and the power reached our requirement, more or less. And the high efficiency klystron had finished the simulation and also the production. The test is underway. I think in a few months from now, we will know whether this new high efficiency klystrons with the efficiency very close to 80%. I think it's 77 or 78%. We are going to know whether this is successful or not. These are other prototypes, including magnets. You can see vacuum pipes and so on. Another R&D we are working on is a plasma injector, because we would like to use plasma acceleration or plasma accelerator as part of this injector to save the cost and to boost the energy from say 10 GeV up to 45 GeV. And by this kind of combination of traditional accelerator and the new accelerator, we can actually overcome the difficulties of plasma acceleration and utilize advantages of traditional accelerator, and also use the advantages of the plasma accelerator to boost the energy quickly and easily and cheaply. So these there are few steps still to be tested in Shanghai or in other places like SLAC. In addition, there's one key point is how to accelerate the positrons. Up to now, most of the studies of plasma acceleration are only focused on the electrons. And a very new idea was just such a team and published at PIL. So this could be a realistic method to accelerate positrons by the plasma system. And this simulation is very successful, and we need to test it at facet of SLAC. Finally, let me report our study of ion-based superconducting magnets. These are all the current available, say, superconducting cables which can be used to make the superconducting magnets. Neodymium titanium is here, so you can see that they can only reach something like 10 Tesla. Neodymium-13 can go all the way up to 16 Tesla. And high TC superconducting materials are expensive, and some of them have, non-isotropic properties. So, which means that, for example, radical, they have two directions. If it's parallel to the field, it's very good. But if perpendicular to the field, it's quite bad. And the idea is to reach this kind of, critical current. So the iron-based cables has been improving over the last several years. So this is the result of short cables in the year of 2016. Sorry. And this is 2019, and we hope by the year of 2020 we can reach here. And this is the long cables. The long cables means more than 100 meters, and which is now. And this curve shows you the improvement of the long cables over the last 5 years. The improvement is, more than a factor of 5. So we hope that in the next 5 or 10 years, we can get this additional factor of 5, and then it is going to, satisfy our requirement. This is test magnet. You can see that this magnet can actually operate at the field of 24 Tesla without much dropping of the critical current. For the detector, you all know that in the past 20 years, people have been many different concepts for the IRC and also for the FCC. So this is a very famous IRC detector and full silicon detector. These are two options for the IRC. And this is the concept, the idea concept for the FCC, mostly by Italian colleagues. So very recently, we had a so-called fourth concept. We haven't come up with a good name, so we call it a fourth concept. And this is actually a crystal calorimeter-based detector. These are the current, design requirements of the detectors at the Higgs factory. You can see them very similar to the IRC requirement. And this is our new fourth concept idea. The key ingredient is trying to improve the energy resolution for EM showers by almost factor of 6 or 7. The way we did is to use crystal as a EM calorimeter, for example, BGO. So the energy resolution for gammas can be improved dramatically to almost 3% over square root E. But because we are trying to have this very new concept of so-called 3D crystal calorimeter, it also have the PFA capabilities. So by having this, we have both very good photon energy resolution and also the jet energy resolution. And we also propose to have silicon and the TPC combined tracker to have a better tracking and also good particle ID, the DEDX. And also we're trying to see if there's need for additional PID detected before the EM carometer. And the magnet is going to be very thin and hopefully using the high TC materials. And for the hadron carometer, we propose to use a scintillation glass with PFA capabilities. And this is going to have a much better energy resolution than normal scintillator, and also better than, say, other choices like RPC. So this is a bit of a design. For example, between the last two layers of silicon, we have a gas tracker, TPC, or the drift chamber. And this kind of detector can give you good tracking from the silicon, but also very good PID using the DDX of the gas detector. We have been working on the silicon pixel sensor. These are all common in all the designs. And we managed to reach a very good, say, position resolution. And also the full-size prototype is going to be built very soon. For the crystal carometer, the most important difficulties is to resolve ambiguity. So the crystals are arranged in a horizontal way, and the incoming gammas is going through this direction. So there's a famous ghost kind of particles. And by using timing of the crystal bars at the both end, we can actually separate we can actually determine the position of the incoming particles, and then resolving the ambiguity. So this one shows the way we are able to resolve the ambiguities of the ghost particles at the distance, say, less than 5 centimeters. So we are still working on the details. And this is the solenoid magnet. I'm going to skip this. For the site investigation, we actually have been looking around all over the China from north to south and many different places. There are, of course, pros and cons. Very recently, 2 years ago, we are actually focusing more on this place, Changsha, which have very good local government support and very good, say, geology and very good transportation. It's only 20 kilometers from the city of Changsha and from the international airport. And indeed, they have direct flight to Europe from this city. And the geology is very good at this site. This is actually the best we have been seeing up to now. And we are still working with the local government to see how to move forward. At the very end, let me talk about synergies with Fcce. So CPC and Fcce have very similar goals and the potentials, even though the two machines are designed somewhat differently and the running plans are not exactly the same. The technologies required are similar, but detailed approaches are sometimes different. So collaborative, say, R&D and the result may help to cut the cost down. The different detector concept may converge in the end to similar ones, and the CPC have trained a large young team for the physics, machine, and detector, which can be used in the future for the future projects. While I maintain a scientific collaboration, we should continue to proceed in parallel until one of the two is approved. So competition can certainly enhance the chance of both. And also the Higgs factor is too important to miss. So we have to make sure that until we get at least one, the other one may have different, say, approaches to decide. So indeed, we are happy to collaborate in all fronts and in all means. So I think this kind of CPC effort is actually useful and needed for the future of high-energy physics in the world. So in summary, CPC Accelerator R&D effort towards the TDR have been progressing well, and we aim to complete the TDR at the end of 2022. The test facility are almost available, and detector concept is still evolving. R&D is going on. Site selection and the civil engineering design in progress, and we are still working with our government to get the final financial support for the construction of the project. Thank you.
Wonderful survey of China activity in this field. Let me ask you a question, though I could even read the paper, but I'm a bit lazy. So can you say a word how you have solved the problem of plasma acceleration over positrons?
Sorry, I'm not the expert of it. And the paper is published in on the PIL. So
yes. I said so.
It's a very complicated kind of design. They have their own, say, simulation approaches and so on to be able to accelerate the positrons. Sorry, I'm not able to explain detail.
Thanks a lot for the talk. I mean, the question I want to ask I think about 5 years ago, there was when people started discussing the circular electron-positron accelerator in China, Yang Jianning, the Nobel Prize of 1957, wrote an article criticizing the project. And this was circulated. There was quite a certain amount of discussion about this paper. Actually, I think Professor Yang is 99 now, I think it's, and actually, if I remember, I'm not sure, you personally wrote an answer to Professor Yang. I think he was making two kinds of objection against the circular collider. One was of a nature of the equilibrium between fundamental science and investment more directly connected to, human problems, say. And a second class of objections were, if you invest in fundamental science, what was the optimum way to invest? I mean, and he was arguing that there were, the same parallel directions that Professor Del Giudice discussed. So anyway, my question is, I don't know if you want to address these objections that were raised. And the question is, in China, is Professor Yang, you managed to convince Professor Yang, is there still a discussion about this concept of if it is the optimum choice for Chinese science?
Thank you for the question. Yes, a few days ago, or maybe a few weeks ago, he had a huge celebration of his almost 100 years of birthday. Although by Western, say, tradition, it's 99 years, but by Chinese tradition, is 100 years. So this is a very big celebration. And indeed, even at that celebration, the circular collider issues was raised again by people and by the media, and of course the Yang certainly maintained his position firmly. His point, not only having these 2 points you just mentioned, there are many other points. For example, he was saying that all the particle physics did not generate any economic benefit to the society. So this is not just Chinese, investment focus. It's even for the whole world that for the pure science, for such kind of high energy scale, there's no point to move forward. And also he was trying to argue that Chinese doesn't have enough manpower. We are not able to have the technologies to build such a machine and so on. So anyway, he has a total of 7 points, and I was trying to counter-argue his points, and of course, in the end, the whole society was divided, and I'll say half and a half, or maybe 4 to 6, whatever, and this actually generated a lot of difficulties for us, and also for the funding agencies. They didn't want to touch this point, so they avoid to talk to us, avoid to make any firm decisions. And indeed, we know that Gian even went to funding agencies, ministers, and so on, to lobby for his position. So it's very hard for us at such a relatively lower level kind of person to lobby for such kind of project. So indeed, we have a lot of difficulties, but we remains to believe that, as I said in the very beginning, what we are doing is right for science. What we are doing is right for China, and whether CPC is going to build in China, or in the end, FCC is going to build in CERN, our effort is not going to be wasted. And this kind of study and R&D and so on is going to improve our understanding of physics, technology, and also going to train a large young team, and this is going to be useful for both China and also for the world.
I have a question myself. Thank you, Yifang, for this. Can you give us an idea of the times for to get to the EP, to the CEPC? Not a commitment, but just an orientation. What would be your guess about the time?
So we started the idea of the CPC in the year of 2012. At that time, we vaguely had the estimate saying that we hope we can start the construction in the year of 2022. Now, time had been passed, was not so ideal, and of course 2022 is too early. And now, from point of view, let's say, the preparation of the design, the R&D effort, and so on, if the government is supportive, we hope that by the time of 2025 to 2026, we can start the construction.
Okay, thank you very much. Other questions? I don't see any other questions, so we thank again Yifang for this beautiful presentation, and thank you very much. And we go now to the high energy linear collider. Steiner Stapner is on the floor.
Okay, thank you very much, and thanks for inviting me to come and give this talk about linear colliders. So I've learned 2 things today. I'm Norwegian, so I learned a lot more about the close collaboration between Touschek and Widerøe. I wasn't so aware of that. Widerøe is, of course, well known in Norway for his scientific work. He's also a controversial person because he worked in Germany before the war and during the war. But I did not know so much about this collaboration and close work together with Touschek, between Touschek and Giudice. So that was interesting. The other thing I learned was that in 1960, it took 2 weeks to make the design of a collider, and this is something we can learn from. I think I will talk about 2 linear colliders, two concepts for linear collider, 2 studies. They are quite mature studies. One is the International Linear Collider, which is based on superconducting RF cavities. So this defines the collider. It defines the gradient. It defines what kind of bond structure you have. And then I will talk about click, which is a normal conducting. It's higher gradient. The pulses are different. The pulses has to be very short, and to make them so short, there's a two-beam scheme, which I will not describe in detail. So you use a low energy, very intense beam to transfer energy and shorten the pulses so they can be used in click. The luminosities are quite different. The International Linear Collider aimed to start at 250 GeV, and the click aims to start at 380 GeV to also cover TT bar production. I will not go more into detail. I'll come back. I will start with click, in fact, because I think there are more recent events in Japan. So I would like to put that at the end, because so that's fresh in the mind if there are questions concerning ILC. So this is one slide describing click. Click is built on this type of accelerator structure, which you see here. It's a copper structure made of this put together. They're 25 centimeter long. You put 8 of them together in a module, and you put 2,500 modules like that. So you only need 4 or 5 kilometers to get to 300 and 380, and then you have the beam delivery systems. Altogether, this is an 11-kilometer installation. And then, as was said earlier, this can be expanded. Click was foreseen. At one point, we thought that what we will see at LHC, first we will see supersymmetry, and that will define the energy scale for the next machine. And then we will see Higgs. We haven't seen supersymmetry. We don't know where the next energy scale is, but we have seen Higgs. So there's a lot more focus now on the initial energy of this machine to be able to produce Higgs and TT bar. Some of these numbers has been mentioned already. It's a 6 billion type of project, which is kind of comparable to LHC. The power is such that it will correspond to 60% of CERN's energy consumption. Power is going to be very, very important in the future. And for both these accelerators, there's a very comprehensive detector and physics studies. And I will just briefly mention them so you're aware of they exist, but I will not go into detail. CLIC was the first accelerator study organized as a collaboration, like we used to do with detector collaborations. Now, all these studies for Future Collider are organized more or less as collaborations. And this is because there are many more universities and laboratories around the world than there was many years ago who can participate very effectively. And in particular, linear colliders, many of these laboratories have small linear accelerators on their own. That's one of the very nice things about linear accelerators. They're scalable. So even a short piece for another purpose than particle physics is very, 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 very relevant for these studies. The parameters, they're a long list. I will not go through them. Stage 1, 380 GeV. The gradient, which is the important accelerating, the length you need to accelerate to a certain energy. The luminosity is going up because the beams are becoming smaller and smaller as you go up in energy. The beams are very, very small. You go down to 1 nanometer vertically and 40 nanometers horizontally at the very, very end. It's a bit more relaxed, if I can say that, at 380. And you can see the length of the installation going from 11 to 50 kilometers. Obviously, I will not go into detail of all this, but this is just to illustrate that, in fact, CLIC is a mature study. Likewise, with ILC, I should say, it has been developed over a long, long time. Most of the critical elements have been prototyped, at least once, maybe 2 generations of cases. And again, for linear colliders, there's a huge strength in the fact that this very same RF technology is being used in free electron lasers and synchrotron sources for the damping rings. And there have been built many free electron lasers over the last 20 years. There are much more accelerators built outside particle physics than inside particle physics. And there are a lot of synchrotron sources being built, which are very relevant for the damping rings of this accelerator. This applies both to CLIC and ILC. Timeline, two points to notice. The construction time is relatively short because it's quite a compact accelerator. Then the idea is to run for a certain amount of time. You can expand partly in parallel, but at some point you need a break to connect and extend the machine. So if you want to do it, of course you can do this differently. You can do different luminosity is ramping up over time for the different energies. So our marching orders towards the next strategy is to have a project readiness report. We have very detailed reports for CLIC already for the previous European strategy, and we will update that. And what I've been told, that if you assume the strategy update in 26, the strategy update will give some kind of guideline, but then one needs a project approval. One could start constructing in 2030. This you could do faster technically, but then you have to put in a lot more resources, and CERN is currently putting more resources in the feasibility study for a big ring. And if you want to have a big ring as an option, you almost have to do that at this point. Otherwise, that will not really be a real option in the next strategy. So I will not go through this complicated. I will just show some example of what we think is important R&D for the time being. This is what is called expand technology. So this is the accelerating structures, which run at 12 gigahertz. And you build them out of disks currently, you stack them together. And the key here is to how you machine these. And we know we have a very good situation for this kind of structure that can be machined by many industries, and it's not really an industrial problem. Then you have to put them together with bonding and bracing, and then you have to test them to very high energies or very high power levels in test stands like this. So this is one key element. Of course, if you can make this better or more industry, easier industry procedures, this will lower the cost and lower the risk of the project. One thing which we are almost struggling with is that this type of compact normal conducting accelerators are very popular. So the closest we have, this is C-band, this is half the frequency, so it's bigger structures. This has been built at TSI, and they built it to an incredible precision, and there's a very good example of what we need to do for CLIC. So we are quite pleased to see this machine working so well. Another thing, and this is led by Trieste, in fact, there is a design study for using this technology for a free electron laser. So instead of C-band, you go to X-band, you make it even shorter and cheaper. And this has led to many ideas of how to use this technology. So this is the compact light, where you can have hard X-ray and soft X-ray in the same facility. This is in fact a 1 GeV X-band linac, which is foreseen for Fcce as an injector to the plasma stages for eupraxia. And we work very closely with the Fcce group on developing this. This is obviously very, very interesting to see the technology being used in such a facility. It was mentioned earlier by Manuela, the idea of using this compact technology for a very short electron linac for a medical linac. Of course, medical linacs are the most common accelerators in the world. And there's also an idea to build a mini light source with the same type of 7 or 8 meter long X-band linac. You collide it with a laser, you get Compton backscattered photons, and you get photon energies, which are very, very interesting. And if you do this very, very well, you get also brilliances or fluxes, which are interesting. So this will be a mini light source, which an academic institution or an industry can have in the basement. So this is a very, very nice thing that we're working on this Linux, that there are so many applications, and in some cases it's a bit hard even to keep the focus on the parameters of CLIC, because there are so many intermediate goals of putting them into smaller Linux. So this is true for superconducting RF as well. So when it comes to luminosity, it is obviously, we're talking about building a Higgs factory. So we need a lot of luminosity. And for Linux, this is really related to dealing with these very small beams, nanobeams as we call them. And this is true for both machines. And what it boils down to is creating a very small emittance beam in a damping ring, similar to they have in synchrotron, extract them with the minimal amount of noise introduced, and transport them and focus them toward the final focus. But this boils down to a lot of different technologies. A key one is stability, alignment, thermomechanical engineering, and this is one of the things which we think we can push further for CLIC towards the next European strategy. And it's equally important for ILC, all this kind of And this is very basic R&D. This was already mentioned by Yifang. In fact, this is common for all accelerators nowadays. That if you look at as a function of different parameters for this so-called klystrons, you really would like to push the efficiency. And there is a lot of very new ideas. He mentioned multi-beam klystrons, but there's also a lot of work on the software to actually simulate the performance, which means that you can push the efficiency. And this goes directly into the wall plug to beam energy efficiency. And we know that there will be a huge push to get down the power consumption of this machine. This is a very complicated slide. I will not go through this, of course. It's just to show that for Click, we think we can run Click roughly at 60% of CERN's energy consumption today at 380 GeV. As you go up in energy, we are more limited. But we're also doing some maybe more ambitious studies, given that this is a machine which works instantaneously, and then you dump the beam. It's very suitable for an energy consumer and energy production which is fluctuating a lot. So renewable energies which fluctuate quite a lot. So what we did a study where we took 10% of the construction cost of the machine and put it into renewable energies and see how often can we run the machines completely renewable. And this is not so easy to do in Geneva. If you do it somewhere else, you can probably run the machine completely with renewable energy, and you will get the energy cheaper because you're invested in the energy production in the first place. We also see if we can run at times when people are sleeping, where the power is cheaper. So I think these are the kind of things we have to do for future accelerators, because it will not really be tolerated that we use energy as we've done before. And if you scale to some of these new accelerators, the energy consumptions are much, much higher already than we already have. Okay, so Click can be extended in length. It's quite easy. I will not go through there, but the critical elements for extension, of course, the physics motivation, power efficiency and the gradient, and obviously the cost. So obviously, if you do it in stages, you can smear out the cost, but it's still costly. This is information about all the reports. We have a very detailed study from the 3TV and even more detailed study for 380. I will not talk about the detector and R&D related to detector. But for a very long time, for both linear collider projects, there are this detector concept, and Yifang mentioned some of them already. And from this, you have a very good description of the detector and very detailed simulation where you put in the detector performance in the simulations. And also what is needed, one is really trying to push the limits. And for example, this is all the R&D related to putting together silicon sensors and electronics in various ways, as hybrid assemblies, monolithic, and also testing this in test bed. So there's a rich R&D program which has been taking place and is still taking place. In fact, now a lot more and more work common with other Higgs factories. This has now been repeated many times for Click as for ILC and all the other Higgs factory. The goal is to get this precision of these different couplings, combining high Lumi LHC and linear colliders to a level where you are sensitive to new physics. And obviously for Click, there's a particular point one can also produce TT bar. Okay, let me move on to ILC. So now we move to Japan. It's a similar configuration in a way. It's a bit longer because the gradient is lower. It's a superconducting RF. And it's in fact, we have a brilliant prototype of that at DESI in Germany, where you have a 17 GeV superconducting machine with performances not completely as needed for ILC, but quite similar. And again, the technology is the RF technology, which is superconducting, and what they call nanobeam, again, focusing of the beam. So I will not repeat that. The goal for ILC is to start at 250 GeV, is because the gradient is lower, is a bit longer, 20 kilometers. The The cost is around 5 billion if you use the same cost we use for other machines, and the power is even lower than for click, by 20% or so. But both linear gliders are substantially lower than the circular machines, just because the RF power in the beam in the linear glider is a factor 10 lower than what is lost in synchrotron radiation in these big rings. So this is the technology. One thing which is particular for ILC, they use the electrons in an undulator to produce positrons. And by doing that, they can not only have polarized electrons, but also maintain some polarance for the positrons. And the damping is longer because the bunch length is longer. You can allow a longer bunch length in a superconducting RF LINAC than a normal conducting. Very complicated slide. I think I've talked about most of these things. As the length, here's the power mentioned. The only point to make is that this machine can be extended in many different ways. It can be extended in luminosity. One can increase the frequency of the bunches, of the trains of bunches. And there's a lot of work going into improving both the gradient and the Q value. So that's the power efficiency in the superconducting RF. It's a very active research area, which will feed directly into the possibility to upgrade these machines, this machine in the future. One thing which is particularly strong, a strong point for ILC, is that there are prototypes of these machines basically all over the world. So I talked about the European XFEL. At SLAC and in Shanghai, they're building CW. This means continuous wave. So it's not a bunched structure, so the gradient is lower, but the same technology, FELs. And of course, if you add up what has been invested in this technology over the last 20 years for the FELs, it's much more than almost any other R&D effort. Of course, this is not R&D. These are very valuable scientific facilities on their own. And I think this alone shows the impact of what is being pushed for particle physics is really spreading out to free electron lasers, synchrotron sources, medical LINACs, and so on. So I kind of disagree with my 100-year-old colleague in China on that point. In Japan, is as you know, and it's not the most stable area geologically, but there is, in the northern part of Japan, there is an area which has been identified for a very long time, in fact, that there's a granite slab, or a couple of granite slabs which are connected, which can make up to a 50-kilometer long, very solid area for building this accelerator. And this is the area which is being proposed, and one has done a lot of work in the area and a lot of work with the local community. There's a product development team in these local communities, but I've also done the seismic survey in various ways, certainly for the first part of this accelerator. So I don't know if you should go into this in too much detail, but the ILC is a very, very international project, probably more than from the conception. And it's really been, to some extent, developed by ICFA. There's currently what is called an international development team, which is trying to push to get into the next phase of ILC. In a way, ILC has been mature for getting into construction for some time now, but one has not managed to make this step to get really to the level one could start the project. So ICFA has made an effort to put together this team in the beginning of last year. And the goal of this is to define in detail what is needed in a 4-year period to get ILC started. And this is quite a complicated matrix of R&D, but more D than R, in the sense that one needs to develop these technologies for large-scale production with the parameters which are exactly what's needed for ILC. And then the construction will be something like 9 to 10 years. And if one could start this on a reasonable timescale, this machine could be ready in 35 or so. Now, it's going to be very difficult to get this started. I will come back to that. So this has been written up in a document. Here you see a description of the work. I will not go in detail. I'll just read the headlines. One key element is, of course, the superconducting RF, as for click with the X bar. But then there's also the electron source, sorry, the positron source, this undulator scheme, I mentioned that. There's an alternative to produce positron in a more conventional way. Damping rings, beam delivery system to deal with the nanobeams. The dump is a very sensitive, even more sensitive in Japan than here, to how to deal with the radiation where you dump the beam. So there's a detailed plan made of this, written up and so on. And Europe is very, very active. These are the European names involved in these different activities. And if you look at the Italian side, it's particular, as you know, there's a strong superconducting activity in Milano, and there's also participation from Fcce in the damping ring and BDS, more in the damping ring than the BDS system. Similarly, for the physics and detector, quite a huge international team, and also here representation from INFN. Minute 40. So I'll just show one example, what has happened over the last 2 to 3 years, and what needs to be happen next in superconducting RF. So the key here is the improvement of the material and improvement of the surface treatment technology. And the goal of this is always the same, is to push the gradient and the Q value at the same time. So you can go higher in gradient without losing power efficiency. If you only do one, you pay for it in terms of the power you have to put into the machine. And this is done not only for this machine, every single superconducting RF in the world will have the same goal. For some it will be more important to improve the Q value, but for others, the gradient, and for ILC, the gradient is important, particularly if you think about upgrades. So this is a huge international effort with many, many groups participating in the US, in Europe, and in Asia. And Yifang showed also how active China is on this area. Here is a little overview of the Milano capabilities, which goes from design, qualifications of cavities, and ancillary components, the facilities to actually test these, and working with industry, in particular Sanon, which is one of the key producers of these superconducting cavities. So I will show 4 slides just to show you how this planning is made. One goes for each item, one goes through what has been done in 17, the last 3 years, and then what is needed to be done in the pre-lab period. And this is then written up in this plan for the pre-lab. So here are maybe the two most important elements, superconducting RF, final focus, how to get this very small beam to produce, but to collide. We have the positron source, also very essential if you want to have positron polarization, damping rings. I mentioned the importance of damping rings. And for, I think I went the wrong way, sorry. And also, for the beam dump is an essential part of this. So in Japan, they're building up their own capabilities. Japan do not have a superconducting larger LINAC, in fact, so they also building up at KT their capabilities for ILC. Again, one very brief plot of what the precision you can achieve with ILC combined with the high Lumi. And you can see one important thing, and this is true for all linear colliders. As you go up in energy, if you can run them at stage 2 and 3 and so on, in fact, these errors go down. So it helps to run them also at higher energy because you get higher luminosities, and you can then reduce the errors on this complex. And this is an example of what type of precision you need. It was mentioned one needs roughly 1% efficiency to see some of these effects, which we could expect from different type of, for new particle or new physics beyond the standard model. This slide is from a recent meeting in Japan by Mikael Pesky. Again, very detailed models of detectors These are the model of detectors which have led it to the click detector, but also, as you've seen, the detectors concept for CEPC. This is all the information about this. I will not go through that, but you have it all here. So what can we expect now to happen with ILC? This is the main question. So all this information has been submitted, and maybe I go use this to describe that. All this information has been submitted to the ministry, which is called MEXT, to deal with scientific projects in Japan, and has been endorsed kind of all over the world. In addition, they have addressed a number of questions from various review committee in an additional document, and there's also a specific request for funding in Japan. But as you can imagine, so there is now an expert panel looking at this, and they've had so far 4 meetings. A very first meeting, then 2 presentations by primarily by the Japanese ILC community and this international development team. And very recently, on Monday this week, there was a further meeting which was more related to questions and answers. And this is important what this committee come out with, because this could allow at least some of the pre-lab funding or the equivalent of pre-lab funding to come forward in Japan, which is very strongly needed to move the project forward. Because if Japan come up with substantial funding or significant funding, then because of the technology interest and because of the wide community involved in this, it would be much easier for the big countries and even smaller countries to participate in such a pre-lab project. There was also a meeting between the ministry in Japan, US, UK, Germany, France, in the middle of October, and there's a summary for this meeting this week. But it's underwhelming in the sense that it just states what's happening. There's no strong statement coming out saying now we do this, this, or that, as you can expect. But if this meeting can be kept on a regular basis, this is really the key for moving the project forward. One thing which is negative is that the ministry in Japan keeps saying that we cannot really put at least too much funding into the pre-lab project until the entire ILC project is discussed internationally. And this is a very, very difficult conditions to deal with. This will be the equivalence of US saying to CERN, we don't participate in the Fcce study until we have agreed on how to fund the Fcce. Then nothing will happen. So to change this, one needs political pressure either from inside Japan or from outside Japan. And this is the current difficulty with ILC. There's a new government in Japan after recent elections. There are some very strong ILC supporters very high up in the government. But there's also, we have to see what a strong supporter of ILC does when this person is high up in the government. Usually then there's push they had at a lower level, they become more careful. But there is a very good time to push this project in Japan because of the favorable conditions in the government. And this is what's happening right now, that one is trying to make sure that this new government is discussing ILC in earnest at the prime minister level and the finance minister level, where one can influence and move money such that a single ministry can say that this is affordable. There was very recently, this is one other development, this is common also for another linear colliders. There was a workshop, and this workshop looked at how could you use a collider facility like ILC, or CLIC for that matter, to the other type of experiment. This was mentioned, diversity, Gian mentioned that one has to have a diverse program. And we know that, for example, light dark matter, couplings, different type of couplings can be studied with electron speed. So one has to look at what is called beam dump experiments in the less than 10 GeV mass scale and very weak couplings to the standard model. Dark matter action, light dark matter action like particles, flavor Higgs Boson, so electron laser collisions, I mentioned inverse Compton scattering, but one can do other type of physics for that. Strong coupled QED, using the photon beams, again for axiom type, ALP type of studies, and also this long-lived particles, which is done for LS. So obviously, if one starts thinking about it, how one can extend the use of such a facility beyond the collider mode, then there's quite a bit of a wider physics program, not only inside particle physics, which can be considered. There's a wide industrial interest in ILC, as you can imagine, and there's also a lot of effort going into making ILC a green facility. Now, quickly at the very end, two more slides about what about higher energies? We can, if you're optimistic, maybe high Lumi LHC come up with something at higher energy. Suddenly there will be an incredible push to push any accelerator electron positron machine to a higher energy. And as I mentioned already, if you go higher in energy with a linear collider, which costs money and power, you can also improve the Higgs coupling mechanisms. But obviously, one can also look at specific models for let me take this as an example, to produce dark matter through a mediator and a specific particle, so it's called Y and X. And one can see what is the sensitivity of a linear collider for this type of dark matter particles. Well, you can see that click at 3 TeV is very, very competitive in some types of beyond the standard model physics. So of course, what is the difficulty of going into higher energy? I mentioned this already. It's the gradient, it's the high wall plug to beam efficiency, and there's something which is often forgotten, which is relevant also for plasma. As you make these beam higher and higher energy, they become smaller and smaller, and things like stability and alignment becomes more and more critical. And energy efficiency becomes more and more critical. Because the more energy you have in the beam, you have to improve the efficiency, otherwise your energy bill will just skyrocket. And there is a lot of work on improving, in addition to plasma, but also improving superconducting RF. This is the single cell gradients as a function of time. And this is a multi-cell gradient as a function of time. And you can see there's a very significant lag between single cell results. But what you can see is that they all go in the right direction. There's going to be higher gradient superconducting RF facility. And this is done mostly by processing of surfaces and material choices, and also processing of the whole cycle of thermally cycling this superconducting RF. But there's also ideas of changing a little bit the structures themselves. These are standing wave cavities. If you can go to traveling wave cavities, maybe you can improve it further. There are some papers starting to come out in this direction, which could push superconducting RF up towards maybe, I don't know, 60, 70 megawatt per meter, which is very interesting. It's almost a factor 2 more than today. But this will take time. You could just look at this curve and make your estimate. But also in the world of normal conducting copper structures, there are new ideas. One thing which hasn't been known for a long time, and SLAC has been very active on pushing this, is that if you cool copper to liquid nitrogen temperature, it turns out you can operate them at higher gradient. And then, but of course, what you still pay is that you have to have a cryogenic machine. And it's not so easy to have a cryogenic machine sitting in a liquid nitrogen bath. And you still have the problem that you need very short pulses for this, because it's copper structures. So there are some very clever ideas now where you try to put a coating, in fact, of high temperature superconductor inside this structure, such that you also increase the energy efficiency of that. And then it becomes very, very interesting, because you can go up in gradient and you can reduce the number of klystrons needed to operate such a machine. So this is very good, and these are very interesting ideas. The summary and thanks. These linear colliders are mature. They are really very feasible machines. The costs are not high, but they're not scary compared to what we've seen. The power, likewise. The timescales are interesting, and the footprints, if you compare to LHC as well, is well within the range of what we can do. In fact, any region can build a linear collider today with either technology. Traditionally, we have associated ILC with Japan and CLIC with Europe. But the fact is, we could build an ILC machine in Europe from a point of view of technology. And the fact is that if the Americans want to go ahead with this cool copper, they could probably build a normal conducting, maybe a liquid nitrogen temperature, if they want to do that. But of course, it all has to be an international project. Now, one thing I really like, in addition, what I like about linear colliders is all the spin-off to applications and so on. You get a lot of RF development because of all the smaller machines. This is harder to do for a big ring. If you have a little piece of a big ring, you cannot do so much. But a little piece of linear, you can do quite a bit. But in addition, if you build a linear collider, then all options are open for the next machine, which is much, much harder to reach. And you are not locked into a size, you're not locked into a time scale. So in principle, you can then, if you improve the RF, you can improve the linear collider. I mentioned some ideas, but also plasma. You can go to a muon collider as a next machine. There's no reason you don't have a heritage of something you need to use. Or you can, if we can build high field magnets with a sufficient low cost, you can build a 100 TeV hadron machine at any size which is suitable when we have that magnet technology. You know, forced to build it for 100 kilometers. But this, I think, is a very good perspective, because I really think we need to keep this option open for future machines. Thank you.
Then, question here.
Thank you, Steiner, for the nice talk. Just a question. You know that there are developments in superconducting cavities, Fermilab. How this can affect, for example, the design of ILC? Can increase effectively either the energy or shorten a bit the machine?
Yeah, it can do both. I think what one is aiming for ILC, instead of 31.5, is to go to 35 megawatt per meter, which evidently mean you make it shorter. But then you have to look at a Q value. So this will have an impact, but probably on the level of 5% to 10% of the entire machine. So many people think that this is really our contingency to make sure we can build a machine with the current budget, instead of saying that this is the new baseline. But the push will be in this pre-lab phase to make that new baseline, obviously, with the highest possible gradient and with the highest possible Q as the default. And obviously, all this will push in the same direction: lower power consumption and lower cost. But they will not revolutionize the project.
Other questions? I have a question myself. I got that click in the basic option is about 6 billion Swiss francs or euros. Yeah. And what would be the basic ILC cost? 5 billion. 5 billion. 5 million. Quite often you see 6 billion because they put in also the personnel in Japan, because that's what they deliver to the Japanese government. But if you do a comparative costing of ILC at 250 and CLIC or FCC, the type of costing we have done, that would be at 5 billion. Sure.
So I'm wondering if the right number is the cost per physicist then participating to the experiments, because here you can, you can put on the beam only one detector.
Yes, correct.
And even if you do this pull out and pull in of two detectors, you double the time you need, or more than double, because you have all the efficiency of the movement.
Yeah, no, that's correct. That's correct. So there are many ways of doing this calculation, but obviously you run with one detector at a time, and even if you do pull-push, push-pull, I guess, you have two detectors. Obviously, this also reduced the cost. I mean, these detectors in the end cost 2 billion each, So this is also a cost impact, but it means you cannot employ as many physicists in the program.
Yeah.
And that's why it's also important to look at this more diverse program in my eyes, because even if we look at now, we think that everything is in the electroweak sector, but it could also be that a lot of the interesting physics is the lower energy and different type of physics. So I think this is generically true for any Higgs factory. We really have to think in terms of diversify. And also keep in mind that this will largely overlap with the high Lumi operation. So there might not be 6,000 physicists ready to jump on this.
Okay. I don't see any other questions, so thank again for the wonderful talk. And I would now give the floor to Sergio Bertolucci. We shift from electrons to neutrinos.
So let me first thank the audience that is still there, and not only the people who invited me. And I have the hard task just to keep you separated from your well-deserved dinner. A couple of weeks after Bruno Touschek died as an employee. And the thing which struck me at the time, just to see that the wave of emotion and affection which was in the lab. Before that, I was working in Germany, and I knew Bruno Touschek for his idea of colliders, and for the bond factor, which was the radiative correction to A plus, A minus. And from a lot of talk with Mario Bassetti, who was spending sabbatical at that time in there. So I came to Frascati just to follow a thing which, that time, you know, when you're young, you think that you are very fascinated by this Renaissance depiction of the physicist, the theorist, the experimentalist, humanist, all at the same time. Then, I mean, it took very little time before some reluctant piece of apparatus not following the elegant law of physics took me away in one direction instead of the other. But essentially, I came to Frascati to work in designing an experiment which was never built on a machine which was never built. And a sort of dry run of Daphne and Chloe. And the reason why was never built is because it didn't have any Greek or mythological thing. It was not after Adone, you build Daphne, you don't build Allah. Okay, so anyway, as Gian has told us, we have this beautiful cathedral of human intellect, which is the standard model. As experimentalists, we are trying just to falsify it with all our effort. And we don't succeed it so far in the sense of just to find the breakthrough. Or two, we all know that it's incomplete because it's not explaining many of the things that we infer or see. And one of them is for sure the fact that not about 20 years ago, we have discovered that neutrinos have mass because through the oscillation. So neutrinos have become one of the hints of the very powerful hint that there must be life after the standard model. And so essentially, I think personally that is a very, very nice period, especially for younger people, because with the Higgs, we have finished all the known unknown. We are now essentially navigating with very good instruments and very many instruments, the vast the dimension of the unknown unknowns. And of course, the synergy between different searches. Also, we experimentalists, we are good in adding dimension to this, and we are adding a lot of dimension to that. So this was recognized since some time in all the strategy, which was brought in by the different communities. Japan, even before there was a measurement of θ13, one of the parameters of the neutrino oscillation, had recognized that it was one of their key line of development just to build a update of a very successful program that they've done in the last 30 years in Japan. And this was also recognized in the strategy update of Europe in 2013. And this brought immediately CERN just to be very proactive in this by building a facility for neutrino, encouraging international collaboration, encouraging the fact that CERN could become sort of hub of Europe for a wider community. And this also had the impact, a lot of impact from in the P5, which was the American reflection, which is happening usually with the time delays of a couple of years. And essentially at this point, it was decided that each region, macro region, Europe, Asia, the Americas should have a sort of flagship program. But the nice thing was that in this case, it was accepted in the case of the American that this program should be run under the CERN model. So there is an infrastructure which is owned by the host laboratory, the host institution, and an experiment which is owned by the international collaboration and not by the local host, pretty much like the experiment at CERN. So it was, at that time, a double miracle. The Americans starting having, adopting for the first time this model, which is not easy and which is not a steady achievement. We are still working on it because they keep sometimes a bit forgetting. And CERN, for the first time, doing a sizable effort outside CERN. And this has been reinforced now, as Gian has shown, in the update, the recent update of the strategy, European strategy. And I mean, it has been reinforced also based on a very factual thing, is that CERN has built a very fundamental place which is the neutrino platform, where large-scale prototypes have been and are being essentially explored, and both for employment in US and in Japan. And at the same time, it has provided, it has contributed in this global organization of our field to the first two cryostats of the Duna experiment. I mean, as soon as we discovered this thing of the oscillation, it was clear just to make a parallel between what happens in the quark sector and what happens in the leptonic sector. And essentially, at the end, if you have a 3x3 matrix connecting this rotation, connecting a mass eigenstate and favor eigenstate, you can get rid of five of these phases, and you can describe this thing with essentially four quantities: triangles and the phase. And there are some complications, because one of the things that since these oscillations are determined by delta m square, you cannot tell whether you are in which order you can put the thing, and this has implication on what then you observe. So you have just to measure. And the other thing is that is amazing is that it was easy just to compare the CKM matrix with the PMNS matrix, and they're vastly different. So whereas in the quark sector, mixing angles are very small, in the neutrino sector, they're big. They're sometimes very maximum. Is there inside some deep lesson that we have just to learn? So essentially, at an accelerator, you're trying just to do things like that. You want just to prove, measure, possibly with high precision, if there is a CP violating phase, because it might have implication for some model for leptogenesis, for instance, and then you would like just to understand why this matrix is so different from the quark matrix. What is the mass ordering is also very important because it tells you about many things about, and besides, without mass ordering, you cannot measure CP violation because it is much more important in terms of its contribution to asymmetry than the CP asymmetry itself. You would like just to understand as good as you can if that matrix is unitary. And then there are other things that you cannot do in an accelerator if you are not extremely lucky. Like for instance, there is something which is so big of Majorana phases that you can measure in some way which I don't even understand how lucky it could be. And for sure you cannot measure neutrino masses, but there are other people. So it's no wonder that there is a large program going on everywhere in the world, and there are large projects being done. So in principle, searching for a CP violation is easy. You make a pure beam of one flavor in one place. You propagate at a distant place. As long as you know how many you are sending and how many arrive there, you can measure, for instance, disappearance, or you can measure the appearance of the other neutrino. You do it for neutrino, antineutrino, you take the difference of these two probabilities and you're done. Unfortunately, it doesn't work like that, because first of all, just telling how many you send, where you send, which energy you send is not a very trivial thing. Second is that because even if there is no CP violation, then since we are done, fortunately, by matter, matter which is traversed by the neutrino is not CP symmetric. So essentially, you will have, since there is a forward amplitude in vacuum, they would propagate, but they don't go in vacuum. And there is the fact that the probability of oscillation for matter and antimatter is different, and it depends on the mass ordering, which is a good thing because then you can use it for measuring the mass ordering, and it depends, and it changes sign for neutrino and antineutrino. So essentially, you see that there are two ways in which you can measure. There are two strategies. One is that you take a short baseline, and then since this forces you just to go to a smaller energy, because essentially the oscillation maximum is a function of L over E. And in this case, you can forget about matter effect. Or in the other case, you take a very long baseline, higher energy, and of course you have just to put more beef into your beam just to have enough statistics. But in this case, you can measure mass hierarchy and CP violation, disentangling the two. And these are the two ways in which they are taken by Hyper-Kamiokande, which is the end by do. Then let me make now a statement at this point. There will be for sure a question. I can already tell you I don't know. I can tell you which one will come first. And I don't know. I mean, it's, in my opinion, irrelevant because these are very long-term programs. They are complementary. It's important just to find precision, and these will be observatory, which are not only connected to the oscillation program, but they have a wider physics thing. And I think that this will be a place. So in a sense, I like this idea of co-petition, collaboration and competition, but I'm very happy that both of these things have been approved. And as I was saying before, is a rather sophisticated thing because you need just to control the systematics. You have just to at the end, you're not measuring probabilities or amplitudes. You're measuring events. And you have just to go from there to the amplitudes, to the probabilities. And then in this case, you have just to know essentially the flux as a function of energy, because you don't have monochromatic neutrino beam. You have just to know the cross-section of the material in your near detector and far detector, and one easy way is that you do a near detector and far detector which have the same type of material, because theorists cannot calculate, nobody can calculate when you have a neutrino interaction on a complex nucleus. It depends on so many things, from the model that you have of the nucleus, on the final state interaction, on the way that, and then you have a detector, which will, regardless of the calculation, will have its own vagaries and things like that. So essentially is, and just to give you an idea, for both these experiments, they have just to improve, if they want just to maintain what they want to do, the way in which we are controlling systematics now by almost an order of magnitude. They have just to go to, say, 7% to the 1% level. So essentially, as I was saying before, it's not only a matter of oscillation and mass ordering, but since this detector needs just to be big, just to have enough statistics to measure this, they can look at neutron decay, proton decay. They can look at anti-nuclear oscillation. They can be there, and if you are lucky, we see a supernova. And this time we will be measuring all the way, because this experiment can collect data without stopping for very long period. They can follow all in real time, all the 100-second minutes, if is needed, hour and then it's a permanent observatory for atmospheric neutrino and solar neutrinos. And then you have a near detector where you can look at very with unprecedented statistics. So you can do a lot of physics, but I will come back later to that. So hyper K, let's start with hyper K. Hyper K is the brother on steroids of super K, and it's essentially increasing this objective by almost a large factor. It is essentially not quite an order of magnitude, but very close to that. It has an enormous amount of experience inside. It's a comparatively simple technology, because you make a big tank of very pure water, is less trivial than it looks, and you put 40,000 photomultipliers just to look at that. And then you can see, in the case that you have you look at the Cherenkov light, and in the case that you have a muon, you see a beautiful ring. If you have an electron, you see a ring which is smeared by the fact that the electron is showering in there. They've proven that they understand very well this technology, and the collaboration is growing, and is already a large collaboration, but it will grow considerably. And of course, they know that they have just to do better than what they are doing now with T2K, because in T2K they have a near detector which is done by a different material than the far detector. So they are thinking of putting together with a sophisticated near detector, a near detector which is done also by water, which is the target of their far detector. Then, in case that the JPark is keeping to what is promised, just to go above 1 megawatt on target, there is a project just to make a second look at the second oscillation in Korea, and this is called Hyper K Korea, HKK, which would also increase. This is still a speculative thing. The other place is Dune, where essentially you send a neutrino beam from Fermilab on a new machine, which is supposed just to evolve to 2.4 megawatt on target. And you send it to a deep underground mine in South Dakota on the Black Hills at 1.5 kilometer depth. This place is fantastic. It goes, is a gold mine, which goes down to 2.5 kilometers, and it has almost 600 kilometers of tunnels. And so it's a fantastic place. There are already experiments there, Majorana and other, because again, it's their Gran Sasso reversed. So it's you don't go there with an highway. Anyway. So it was formed at the beginning of 2015, immediately after there was the completion of this strategy update from all the regions. And it is now essentially grown already to more than 1,300 collaborators. I can skip now many of these plots, which are interesting mostly for people who are essentially very much inside this. But again, what I would like just to show is the fact that in this case, even before building things, you have just to be very conservative and not to be carried away by a very optimistic simulation. You have just to try just to think that nature is much smarter than you and find a way in which it can make a fool of you. And we have discovered a number of them already, and we are keeping doing it. But anyway, looking at the thing, is clear that we need a lot of mass. So we need 4 of these detectors at the end for having a fiducial mass, which is about between 40 and 50,000 tons of liquid argon. And then it's also clear that we have the chance to solve mass hierarchy pretty fast in a matter of 1-2 years if everything works, even with not a complete detector, and that it will take 7 to 10 years just to give a reasonable measurement covering all the possible parameters, let's say at least 3/4 of the parameters of CP. I skip this, and I keep this because this is just to avoid the question. Is essentially this the comparison, which means very little. Everybody has just to sell the project at home. As a matter of fact, we will be collaborating in many aspects. We will be collaborating on how we make these beams, because if you think that sending 1.3 megawatt on a target is an easy thing, you're wrong. And so, I mean, Japanese and Americans and European have a lot of experience in that, and it's not a trivial thing. We are collaborating in many other aspects, for instance, of simulation and modelization. We are collaborating in the fact that we know that Hyper-K knows that if we measure mass hierarchy, we give them a big hand in telling CP violation. And the complementarity doesn't stop there, because, I mean, Hyper-K has a bigger mass. I was showing you 180,000 tons, but can see proton decay, for instance, only if the proton decays into particles which emit chunk of light. A liquid argon detector, which is essentially an electronic bubble chamber, can look at that even in other topologies. So again, it's complementary. The same goes for the NN bar oscillation. And also in the case of supernova, there is a complementarity between the two, because we have proven in big prototypes at CERN that we can do very well in very low energy electrons, and we can tell them. So it is so INFN has decided just to be engaged in both programs, in one a bit more strategic, and also because it started before, and the other one, which sees a participation since a long time to the Japanese part. We will keep doing that because, again, INFN thinks that is a value just to be present in this field in all the experiments. And the contribution of INFN is not only to the experiment, but also to infrastructure. For instance, we are providing part of the RF cavities where Italy has some knowledge, as Steiner was saying before, to this 800 MeV LINAC, which is the pump for getting to these 2.4 megawatt beams. And the contribution of INFN has been fully recognized by DOE. There is a memorandum of understanding on the table, which recognizes that INFN is bringing in a value which exceeds, in their way of accounting, more than $120 million. Unfortunately, it's not that the INFN is giving us the experiment under $20 million, but I mean, it's and what we have just to do there is just to build 4 of these cryostats. If you look at the dimension, is 66 meter by 19 meter by 18 meter, and again, these are things which can be built only because you cannot just build the prototype the size of this table and then scale it up to a thing like that. You have just to make sure that you know what you are doing. Also because these are not evacuated cryostats. Usually when you put vacuum just to insulation, these are done like you're making ships which carry liquefied gas on, and they are made by steel, insulation, and this membrane that when the gas liquefies are done in such a way that they can keep all the stresses away that don't break. And you can make enormous things like ships for that. And there are 2 companies in the world who have developed this technology of the thing. And one of these companies in Europe and is working with us. And of course, they had other standards. If you have small holes in this membrane in a ship, who cares? You use the gas that blows out just to run the turbine. You cannot do that in a liquid argon experiment. So at the neutrino platform at CERN, we built a couple of these objects in which we tried the real size engineering prototype, which will go into the final experiment. And this technology is based on a thing of which, again, we are proud because it was started by Carlo Rubbia. He had an idea in the 77. And essentially, you're making a TPC into the liquid argon. You have a field which is about 500 volt per centimeter from cathode to anode, and you drift the ionization of a crossing charge particle in such a way that you can reconstruct it 3D. And at the same time, since you're measuring the time, you need something which gives you the time, the start. Is a clock, so it's a chronometer. So you have just to collect. Fortunately, liquid argon emits a lot of light. It emits about 40,000 photons per centimeter for a charge track going into it. And so you have just to have a system which collects the light when and starts the clock for counting this drift. And this is done, and is where also Italy has a big... Now, with all this prototype at CERN, we became more and more, we started taking away things which could be done in a different way. And now we are doing this vertical drift in which we divide this huge volume in 2 parts, and we drift upwards the charge, and downward in the other, and there is a cathode in the middle. The reason to do that is that then you can put, instead of putting these wires, you can put a sort of printed circuit, which is much easier and much cheaper and much more solid. And the second thing is that you use more volume because you have a less encumbering thing inside. The bad thing is that you need just to drift for a longer space. And if you remember what I just told, that you have 500 volts per centimeter, 6 meters is 300 kilovolt, and this is not an easy thing. The other thing that we have just to care is the near detector, and there we have done the near detector is composed by 3 parts, and these 3 parts are essentially 2 of them are moving off axis in such a way that they can explore a narrower band of the beam energy in order just to keep systematic, and 1 part stays on axis for 2 things. First, just to try to measure all the shape, the energy, the profile of the beam, and the second is monitor the beam that is not. And for doing that, we are recycling 1 experiment, which is in Frascati, which I contributed to build as other people here in this room. And this is this experiment, which, by the way, still has a beautiful magnet, 6.6 Tesla magnet, and it has still the most sophisticated sampling calorimeter ever built. Which has a fantastic, very good energy resolution and fantastic time resolution. And of course, we have just to do in reverse this thing that we were doing when we mounted it, and bring it over there. And just to tell you that we are not bringing there a piece of old equipment. These are the performances of Chloe as measured, which stopped doing physics in 2018 when he stopped, and they're equal to the one at the beginning. And look at this, 58 picosecond for 1 GeV electron impinging. Inside, we will put a tracker and another piece of apparatus, which is a nice object. We want just to put in there also a small amount of liquid argon, because we want just to measure, not because we want just to mimic what is done already by the other liquid argon detector, but because we want just to measure what is produced in a magnetic spectrometer, which is in there. And in this case, we are developing a detector which doesn't have inside the drifting of electrons, which is very precise, but is very slow, but reads the track like just going to the movie. It takes picture with cameras, because they are liquid argon emit slides, and reconstructs the track by just taking stereoscopic pictures. I will save you all these performances. We are developing the prototypes, we are developing all the things, but we essentially, we are also developing very accurate simulation, not to be too optimistic. But I want just to conclude, just to give you the fact that we have detectors which will be exposed to unprecedented flux of neutrinos, open different possibilities. We can do really deep inelastic scattering and with neutrinos, and we can do a number of measurements which have been the dream for even for not only for new physics but for systematics, for structural function, for whatever, and it can be done as a bread and butter from the day one while you are waiting to accumulate the statistics for the oscillation. And on top of that, there is ample space for surprises, because for instance, we are definitely putting together near detector and far detector. We will set new limits for sterile neutrinos. We will look at dark photons. We have a long list, and I encourage you we just published a paper on that, just to go and see. So to conclude, I think that by the time in which the neutrino became massive, they are a very good way just to follow, just to see what is there. And I think that now this generation of new experiment will constitute a very valuable tool for indicating where we are going. And I hope that we have the first hints soon. And in a sense, this is a thing that will occupy younger physicists for a long time, because as I say, these are observatories more than is a long-term problem. Thank you.
I have a question myself. What is happening with Juno?
Oh, Juno is proceeding very well. I mean, Juno wants us to measure essentially other things. And, you know, Yifang is a very prudent person, but he's very smart. And he was behind the Theta 1-3 in Daya Bay. He was one of the leading people there. So in principle, Juno is progressing well. They will give another nick in the precision of Theta 1-2 and putting together. I mean, if they are lucky, they could just get 3 sigmas if the CP is maximal or things like that. Again, there is a problem of mass hierarchy and things like that, so they are trying just to get smart also on that.
What's your view about the status of LBNF in view of this Build Back Better Act? And you think that it's going in a direction of repeating the history of the SSC?
Well, you know, if it does repeat the thing of the SSC, I think that also CERN will need also plan C and D. And because it's probably starting a long landslide which will not stop at Fermilab. I think that the Americans are in the typical confusion in the moment. In this moment, the situation, as I understand it, is that, you know, the thing was quoted at 1.85 billion. There is a rule which, if you exceed 1.5, the baseline maximum fork, which was 1, then you have just to, before doing the CD2, which is the baseline cost, you have just to do a CD1 RR, which is a revision and reflection. They're doing it for something which is probably less than, would say, 70 million in their accounting, over 3 billion. I mean, if you ask an Italian about the foresight on a thing like that, they tell you, it's like, come on, don't, you are kidding, and they send you away. In America, it's not like that in this moment. So we are going through a CD1 RR in April, and then everybody believes that this will be successful. We'll go to the CD2A. Probably they will give them a bit more money. The problem is that in US, contrary, that's the advantage of CERN, every time there is a change in the political setup, there is a 1 year, you lose 1 year. You lose 1 year because they are changing all the people, all the political, the spoil system. And still, US is under continuing resolution, which means that is, on the good side is that they did not stop the excavation. So if they do it like the SSC, they've already spent 800 million on this thing. So it's, I don't think it will stop. We have just to avoid that it comes too late, because the power of this thing is that it comes, I don't care, 1 year before, 1 year later, but not 7 years before. It is impossible, 7 years later. The two programs They have just to go very much. But it will be thing. And as you are well aware, it's not only dealing with neutrinos, it's dealing with high luminosity, LHC, and many things. It's a bit of confusion. The funny thing is that it's a counterintuitive way. Every time there is a Republican president, we think that they don't care about science, and they don't care about our science, but they give us money. Every time they come, the Democrats, they think they have good ideas, they have fixed ideas on science, and they cut the money to fundamental science. It happened with Clinton, it happened with Obama, it is happening now with Biden. So it's not a good reason just to vote Trump. No, don't misunderstand me.
And we can go to the conclusion, which would, if there are, I would ask if there are people that want to make some personal recollection of Bruno and say something about that. Yogi.
Giving me some time. I've told already Francis my first meeting with Bruno Touschek when I came to your university for the first time, and Nicola had just left for CERN. So he was very kind. He said, you can occupy my office while I'm away for a month or 2 months. Of course, I was being a young man, it was such an honor. My prestige went up with my colleagues. And then one day, while I'm working there, somebody knocks, and I say, come in. And here was this gentleman whom I didn't know. And he said, who are you and what are you doing here in Nicola's room? So I didn't know who he was. It was quite clear he was someone very important, but I did not know. So I said, well, the professor has given me some space to work during his absence. And then he said, what do you do? So like a student, I of course started to answer him and so on and so forth. Okay, let's go get a coffee and so on. And we became very good friends. I used to play badminton on top of their thing, and he will talk to me about his British friends who were in Rome, and he will say some of them had been to India and they were sort of experts, and he would say, is that man real, or is he just talking like that? And I must say, I did not have the privilege like many of you have, of having him as a colleague and as a teacher and so on, but I just revered him for, not only for his knowledge, but for the way he imparted things to him. And then one last point, which is the following. While looking up, as you were organizing this conference, I started to look at the Touschek effect outside particle physics. And I found that there is a software that's called Touschek Lifetime. Now, guess where they use it? When there is, in a city like Rome, there are places where some electricity, big grid comes in and then power gets distributed, there are a lot of losses. Well, they use the Touschek effect, not in the way that beam people use it, but they have not milli, but thousands of amps. And all of this energy that is getting dissipated, and there is, people sometimes call it the Touschek resistor. And they actually use, there are these phenomenological formulas based on his calculations. So I just wanted to mention it to you.
Okay, we are all tired, and it seems that there are no other interventions. So I would like simply to express my great satisfaction about these 3 days. We have learned a lot of things. We had wonderful talks and wonderful discussions. And so I would like to thank all those that collaborated into that, including the personnel that helped us at Lincei, and of course Istituto di Fisica and in Frascati. And I would like to wish you all a good return home, and thank you very much.